Hello everyone, my name is Yew Long Tat. So I'm going to present to all of you about the laser diode performance influencing factors in my this is my title for NE 504 project and presentations. These are my selected journalists. The first one is a laser diode optical output dependence on junction temperature for high power laser systems, HPLS. So in this journal, we'll discuss about the influencing of the junction temperatures to the system, to this system. And second, the reduction of beam divergence angle in the laser diode array with large mount using a BTS, beam transformation system. So we'll just discuss about how we are transferring or to change the beam transformation system to reduce the beam divergence angle and how this will impact the laser diode array performance. Thirdly, the investigation of photoelectric performance of laser diode by regulations of P waveguide layer thickness. So we'll discuss about how this change in layer thickness will impact or change the photoelectric performance of a laser diode. Okay, let's start with first journals. So laser diode optical output dependence on junction temperatures for high power laser system. Okay, the executive summaries. The HPLS, high power laser system, as we know, it uses the laser diode to pump fiber gain media to produce coherent laser light. So because of the coherent laser light, the heat produced from this system will be very high. So this will be a main limitation in HPLS design, because a lot of waste heat will be produced during the operation, and it needs to be managed to improve efficiencies, because a lot of times the thermal management is important, to handle this heat, so that to improve our system efficiencies and effectiveness. And this waste heat in laser diode will lead to an increase in junction temperatures, which we will discuss about in this journal. And this increasing in junction temperatures will lead to a drop in optical power and spectral output shift in this system if the heat or the thermal is not properly controlled. Okay, in this paper or in this journal, so we will simulate the interactions, when the junction temperature increase, how it will affect or impact the threshold current and slope efficiencies, central wavelength and full width half max, these diode parameters, and how this will impact the final optical performance from the system, high power system. So before we can simulate the system, so we need a lot of predefined parameters or to define the equation required to be input in the simulation tool, simulation software, where you can see there's a lot of predefined parameters in these tables, but I will not go through all. But there are 4 major diode parameters that we will discuss in details, to check the interaction of it when junction temperature increase. What will be the impact on threshold current, on slope efficiencies, central wavelength of output, and full width half max of the output. Then how this parameter will impact again to the output or the diode output of the laser diode. As you can see, we will use the predefined parameters in previous table to derive the equation that we will use in the simulation model, to be input and to check the interaction of the junction temperature with the threshold current and the slope efficiency. Right. I will not go through all these derivations, so I'll just state here for you to at least understand. You can look at the derivations formula here, from here, then on the other hand from here, in order to generate the final equation here to be input into the simulation software. And for your information, from these two equations, junction temperature and optical power, so we can relate a bit from this equation that we can see some interaction already when junction temperature increase, the end slope will reduce, so end slope will be reduced, then and followed by the threshold current will be increased. This is a threshold current will be increased, and this lead to an overall decrease in the output or optical power of the system. So that's about the threshold current and slope efficiency interaction with the junction temperature. So this slide will discuss about the center wavelength and the spectral width. So these are the equation of the interaction between center wavelength with the junction temperature, and also the spectral width and the junction temperature. So, and how will this impact the power output of the system? So is explained in this equation as well. So in general, in conclusion, when junction temperature increase, the center wavelength and the spectral width both are the same, will be reduced, and this will lead to an overall decrease in the optical power value in the system. So you can this is just for reference. You can look at from the literature. So there are a lot of laser diode type, and this is their center wavelength and spectral width value. So you can look at it. This is the entire process of modeling of a high power laser system model to simulate the optical power output. So those equations that I've shown earlier will be input into this model in a simulating software to simulate the output of HPLS. So you will see two types of output here, optical output and heat output. Those powers that not converted into optical will be in terms of heat. Okay, we'll run the simulation in three cases. The first case is to run the HPLS model without inclusive of the four major diode parameters. Okay, no the previous four parameters that I mentioned, including the threshold current, slope efficiency, center wavelength, and spectral width. So we will not include in the first case. And second case is to run the HPLS model with only center wavelength, include only center wavelength. And the third case is to run with all the four junction temperature dependent parameters will be included. So this is just to make a reference from case 1, make a reference output from case 1, and to check only this wavelength parameters, what is the output, and compare with all four, just to differentiate on the output from each matrix. Okay, then we can talk about the result and discussion. So this is the case 1 optical power output without junction temperature dependence, the four diode type parameter that I explained earlier. So you can see this is the optical. So previously, in terms of opticals, in HPLS, there's three types: laser diode optical, gain media opticals. But what we need to focus is the optical output. Yeah, this is the overall optical output that is come out from the HPLS. Okay, this is important. For the case one is very important because it gives an idea of the best performance, the reference performance of our HPLS the system can achieve. So without any disturbance from junction temperature. So there's no performance degradation. You will see a straight line here over a period of time. So just for your information, the optical output is actually calculated from optical gain media minus the heat combination of heat. So the heat result I will explain in next slide. Yep, this is the heat generation from the HPLS system. As if you remember, I mentioned about those power that not converted into optical power will become heat eventually. So you can see the heat in this first case is also constant because of no inclusion of junction temperature dependence. So just for your information, the heat of gain media is from the optical laser diode minus optical gain media. So this is just for reference, and this is the heat number. Okay, so this is the result for the case 2 optical power output, where you only include center wavelength, temperature dependence, diode parameter. Then we can see there's no longer a constant power output like in the case 1. So we can see some degradation here. Okay, from the 5 second for a certain of period. So I'll go through again in the summary, from all these cases results. Then you can see more clearly in the later slide. I'll just go through all these results as of now. Okay, this is the second case, heat generation result. So you can see as there's a degradation in output optical power from the previous results. So you will see some rays in the heat gain media here. So for this period of time. So there's no longer a constant heat generation as in the first case. This is the case 2 junction temperature. We also simulate this, and you can see the junction temperatures is changed around 16K, from 5 seconds to 12.5 seconds here from the activation pulse. So there's a change, and yield a drop in optical power output of 5 kilowatts from previous results. So I will still just go through here, and you will see a summary in the later slide. And this is the third case of optical power output results here. So it shows even more degradation now when we include the 4 junction temperature dependent diode parameters, as well as case 3 heat generation. So it's no longer constant, right, like in case 1. So this is again inclusive of all junction temperature dependence diode parameters. So this for the third case, it caused even more temperature change, from the activation pulse here. It's around 17K now. So and also yield a drop in the optical power output of 7 kilowatt. As mentioned, This is the summary of those previous results for 3 cases. So the case 1 without junction temperature dependence parameter, and case 2 with only center wavelength, and case 3 with all 4 diode parameters. So as simulated, the output is there's the optical output of first case is 50 kilowatt. So this will be the best performance of the laser, without any degradation caused by the junction temperature. We assume the junction temperature is perfectly controlled in this case. So the second, when we go to second case, the optical output will drop to 45 kilowatt, which percentage change is about 10%. Okay, and the third case is drop even further to 43, and the change of percentage is around 14. So all these are compared to the case 1, first case. Okay, and as explained as well in previous slide, so the junction temperature change for the second case is up to 16 Kelvin, but to third case is just slightly higher, okay, to 17 Kelvin. Due to, when we include more diode parameters, then you will see a slightly larger junction temperature compared to case 2 and case 1 as well. When we look into the second case, spectral power density curve, where we only include the center wavelength parameters, so you will see the result is they are slightly shifting in the wavelength, the output spectrum. So this is for the case 2, and it will still have the same peak intensity, compare with the nominal curve. While for case 3 spectral power density curve, when we include all 4 diode parameters, we can see not only the spectrum is shifting, shifting in wavelength, and also the output, the optical power level are different, and as well as you can see the spectrum full wave half max is actually expanding. So meaning that the laser light intensity is now degraded. Okay, degraded. Okay, this is the interaction profile for all the interaction between all 4 diode parameters to the optical power output of the system. So we have threshold current, we have slope efficiency, and we have a center wavelength, as well as the spectral width. So discuss about the outcome in the next slide. So from the interaction profile, where we have 4 parameters, to the interaction of 4 parameters to the output power. So we can see all 4 parameters did impact the output power, but among all 4, center wavelength has the most significant effect on the power output. So as you can see as well, for case 2, where it's only center wavelength, we can see a power drop and a significant junction temperature drop, to 10% and to 16 Kelvin respectively. But compared with case 3, where we add on another 3 parameters, it's only very small influence on the output power drop and junction temperature rise, which is only around 4% increase in power drop, and only 1 Kelvin increase in the junction temperature. So for certain laser diode application, so a laser light intensity is very important, is significantly important than the output optical power. So a reduce in optical power can be acceptable, but not for the reduce in the full wave half max, or the light intensity for some application. So as conclusion, so we can see, and when we include all four parameters, then we can see a significant degraded of power density. So in this case, I would say all the temperature dependent parameter, all temperature dependent parameters need to be included in the simulations equation or the modeling, so to really understand how junction temperature can affect the laser light output, or the output, the power output and the light intensity. Okay. For journal 2, reduction of beam divergence angle in laser diode array with large mouse using a dual beam transformation system. So we will discuss about how they transform the BTS, beam transformation system, in order to reduce the beam divergence angle. So the application of laser diode array is often limited by a large SMAU. So large SMAU, you can refer to the below picture here. So this is often occur when there's a series of emitters, or laser diode emitters arrangement that do not follow an exact line, or sometimes it's due to thermal expansion coefficient mismatch between bar and heat sink during the die bonding, and this will lead to increase in the angle of divergence after the FAC, fast axis collimator. So in this research or journal, so we use, they use two angle half BTS to compare with a full BTS, in divergent angles, to improve the divergent angles. We try to avoid a large angle of divergence, to have more concentrate or coherent output of the laser. And at last they compare the coupling efficiency as well between the angle half BTS and the full BTS. So we need to set up again a simulation model by using a GMAX software. Then we will have a full system here with a series of large SMAU diode, and we collimate with two angle half BTS over here. So the parameters is shown in the table below. Okay, you can look at it. Then we can calculate, so that we can calculate the angle of divergence of the laser diode. So we actually create two types of SMAU. So one is, we call it parabola, and one is S shape. So you can see a S shape here, the emitter position, and another with parabola shape here. So you can look at the parameters of the laser diode bar, over here in the table. So this is the linear displacement relationship between the full BTS and the dual half BTS of parabola and S-shaped SMAU. So you can see full BTS is the Y displacement, only Y. Okay, and two half BTS is actually the Y displacement, Y2 and Y1. So this is a parabola. This is parabola type of SMAU, and this is a S shape. So in geometric optic, the deflection angle theta is defined. You can calculate the deflection angle theta by dividing the linear displacement Y over a focal length in FAC or BTS. So when we have the setup ready, then we can run the simulation and obtain the divergent angle from both axes, fast axis and slow axis. Then compare for both type of BTS, the full and the dual half BTS. So the divergent angle is defined as a divergent angle equal to a spot diameter in CCD over focal length. Focal length here is referring to this spherical lens to the output here. So by looking into the equation, so the reduction of the divergent angle is actually depend on the decrease of the linear displacement. Then we set up, previously is run by simulation. Then in this journal we also they also set up an experiment to actually measure the divergent angle and coupling efficiency, then compare both BTS. So you can see here, this is a full BTS beam shaper, okay, and this one divide into two, which we call it half BTS beam shaper. So they have three type of bar, which is a parabola type of smile. So this is the two view of the axis. The first one is a fast axis, and the second one is a slow axis. It's kind of fast axis is like the y-axis, and slow axis is the x-axis. Then we can calculate the angle of divergence over here, divergent. So the lower the divergent angle, the better the coupling efficiency. So let's discuss about the result and discussion. So the red line indicates the half BTS or FAC, and the black line indicates the full BTS. Okay, then this one is for fast axis diameter and with parabola form of smile. The angle of divergence of beam transmission is improved, or will be lower in half BTS compared to a full BTS. The number is around 6.35 to 2.23 milliradian. So the residual angle can be reduced by around 64.9%. So again, the full summary will be discussed in the later slide. So this is the slow axis diameter, again with a parabola form of a smile. Same results as usual. We will observe a better or smaller residual angle of divergence of beam for half BTS compared to a full BTS. So this round we reduce about 40.6%. Let's go to S-shaped form of a smile with a fast axis diameter, and as the same results for half BTS is smaller. We'll have smaller angle of divergence of beam compared to a full BTS. This round is around 50% reduction. While for S-shaped form smile with a slow axis diameter, so again the half BTS is better than a full BTS, but this round the angle of divergence is just improved or reduced by around 25%, 24.7%. So again, this is the summary of the simulation result that I shown in 4 slides earlier. Parabola and S-shaped form of smile, we compare between full BTS and half BTS. Okay, then you can see a reduction in fast axis divergent angles for around 40%. This is for parabola, while much higher reduction in S-shaped form of smile. So, but both are the same result, that half BTS is better, with smaller divergent angles than the full BTS, as well as intensity. Half BTS has a higher intensity than full BTS, same as S-shaped smile. So in slow axis divergent angle, we have reduction in around 50% for parabola, while S-shape is just around 25%. So as usual, we have higher higher intensity in half BTS compared to full BTS in both cases. So they also have an experiment result to compare the result as well. So they actually use 3 bars with the smile in a parabola shape, and they compare full BTS with half BTS. So you can see the result is quite comparable. Fast axis is around 10, 9 to 10 is comparable, 9 to 10. When compared to half BTS is around 6 to 7. 6 to 7 is also comparable, 6 to 7. So when we compare here, the result is quite comparable, is consistent here between the simulation and experiment. So as well, they compare the optical to optical coupling efficiency. With a lower angle of divergence, you can see a higher coupling efficiency with a half BTS compared to full BTS. So as a result, when we compare parabola form of a smile of the laser diode bar for angle of divergence, compare with between two half BTS and the full BTS, so the results show consistent between experiment and simulation. Okay, and in the experiment as well, when we compare coupling efficiency, we can see a better performance of coupling efficiency by dual half BTS compared to the full BTS. So by comparison, it's increased more than 85%, which is an improvement of more than 4% comparing both half BTS to full BTS. Let's proceed with third and the last journal. So this is the investigation of photoelectric performance of laser diode by regulation of a P waveguide layer thickness. So how is the change in layer thickness will impact the photoelectric performance of laser diode will be discussed in this journal. As we know, there's an increasing demand on power and optical properties of laser diode. So in order to obtain or achieve a high power laser diode, the optical power conversion efficiency is a key issue. So the current or the conventional way to reduce the internal loss, to improve the power conversion efficiency is by a symmetric waveguide structure. Okay, but this is will be resulting in a poor far field characteristic because of the broad waveguide is prone to high order transverse mode operation. Okay, but to increase the waveguide layer thickness will also increase the resistance, where it will also limit the power output. So in this paper, we'll find out the optimized layer thickness to achieve high IR output as well as electrical to optical conversion efficiency. So again, to generate a simulation model, so we need to know some theoretical analysis of the equation that we need to input into a simulation software. So in order to calculate the power and conversion efficiency from laser diode, these are the equation. So above threshold, the output power is this. Okay, while the power conversion efficiency is this. So I'll not go through in details on the derivations, so you can look through it. In order to calculate the peak conversion efficiency and the peak power output, so we need to derive the efficiency, conversion efficiency with respect to the current. So equal to 0, that means the current at which the conversion efficiency is the maximum. So with this equation, then we can derive and get these two peak power output and the peak conversion efficiency equation. So from above analysis, in order to obtain the high output power and the high power conversion efficiency, we need to ensure a low or the decrease in threshold current, optical loss, and voltage, while need to increase the internal quantum efficiency and the slope efficiency. So, and after this, we will discuss about the influence of the P waveguide layer thickness on the laser performance. So, with all this equation input to the simulation. Also, in this journal, the authors also set up an experiment to actually measure the optical and electrical performance of the actual device, just to compare with the simulation. So the laser epitaxial wafer was grown by a metal organic CVD on gallium arsenide substrate. So I will not go through the structural parameters of laser, you can have a look on it. So this is the device fabrication methodology, where a contact strip was produced by lithography and etching method to remove the gallium arsenide contact layer outside the strip. So silicon oxide passivation layer was deposited by plasma enhanced CVD to prevent a current spreading. Then we deposit this material as the P electrode and N electrode respectively. So finally, you can look at the schematic of a laser with a structure in here. This will be the device structure that will be produced with a specific layer thickness after we got optimized layer thickness from the simulation results to be proved in experiment. Then this is the single laser chip that they used for the experiment, and the cavity length will be 2000 micrometer with a 20% fill factor. So will be proved with theoretical results, whether that particular layer thickness, with that thickness, what is the output power and the power conversion efficiency. So in the simulation software, so actually they alter the P waveguide layer thickness in 250, 350, 450 to 950. So let's start with the first results, where we compare the interaction between P waveguide layer thickness with the voltage. So as you can see, voltage increase with the increase in P waveguide layer thickness. So because of the carrier mobility of the P waveguide layer is lower than in the N waveguide layer. So as you can see as well, for 500 nanometer, so those are thickness below 550 nanometer, the voltage will increase obviously. That means a bigger increment, below 550, while above 550 thickness, the voltage will increase just slightly. So the reason is the layer thickness is constant and resistance difference gets smaller between P and N region. So when we look at threshold current interaction with P waveguide thickness, so the thinner the P waveguide layer, the higher the threshold current. But actually laser diode with asymmetric waveguide structure is required the thinner waveguide thickness to reduce the series resistance. But if we get too thin, the layer get too thin, the internal loss will increase due to the non-radiative recombination increase, which will result in an increase in threshold current, so which we don't want. So this is the optical loss interaction with the P waveguide layer thickness. So as you can see, when the layer thickness go thinner, the optical loss will be lesser. So the layer thickness is very important to influence the photon distribution in quantum well. So when photon outside and in quantum well are absorbed by free carriers, it will result in optical loss. So this is regarding the interaction of internal quantum efficiency and the non-radiative current density with interaction of the different layer thickness. So as you can see, figure A here showing the highest highest internal quantum efficiency is actually 550 nanometers here. Higher, maybe it's not that clear, but it is highest. And the non-radiative recombination, the minimum will be be inversely proportional, that the lowest non-radiative recombination will have highest IQE, internal quantum efficiency. Yes, will be 550 nanometer. So this is the interaction plot for the Auger current density, SRH current density, leakage current density with the different P waveguide layer thickness. So as we know, the Auger and SRH recombination are the major contributor to the non-radiative recombination at the active region. So when looking at the IQE results in the previous slide, so when the P waveguide the thickness varied from 250 to 550, the non-radiation recombination is mainly due to the Auger recombination, while when the thickness varied, increased from 550 to 950, the IQE is mainly come from the increasing of SRH and the leakage current. You can recheck back with the IQE result in the previous slide. So from previous output, we can actually compute or calculate to obtain the power and conversion efficiency. So by comparing from all range of layer thickness, P waveguide layer thickness, so actually the end at the end, the 550 is actually achieving the highest power output with the best conversion efficiency. So as you can see from the figure C and D in the previous slide, the results shown that the maximum output power and maximum conversion efficiency is obtained at 550 nanometer, because when you can see, as I highlight here, when the layer become thinner, right, from 550 to 100 nanometer, the non-radiative recombination will be high because of this Auger recombination, which cause the output power to decrease. And this is because of the layer, when the layer become thinner, more holes are injected in quantum well, so the carrier concentration is increased and therefore increase Auger recombination. While on the other hand, when the layer become thicker, from 550 to 950, the output power also decrease because of the increase in SRH recombination. So that's why the highest conversion efficiency and the highest maximum output power will be in between 550 nanometer, right? And as we know as well, the electronic optical conversion efficiency will decrease as a result of increasing the voltage and internal loss. So the maximum output power and conversion efficiency can be obtained at this number, 550 nanometer, from the result. So again, an experiment is set up to produce or fabricate the 550 nanometer device and to measure the PIE characteristic to again compare with the simulation results. So as you can see, um, the threshold current of the measurement is actually 0.85, okay, 0.85 ampere, which um, is a kind of difference from the simulation of 0.65 ampere. You can look back to the previous threshold current chart. So there's increasing of threshold current is believed to cause by an increasing inner loss due to impurity in experiment compared to theoretical results. But for the power and the injection current parts is consistent between experiment and the simulation, where we obtain the maximum power output of 5 watt with injector current of 5 ampere with the optimized P waveguide thickness of 550 nanometer. So there's 3 journals that I go through. Previously that's all, and to summarize here, so we do some comparisons of the in terms of novelty, methods, and results. So from the first journal, the novelty is the mostly the experiment and the modeling work has been done describing the two phenomena, optical power drop and spectral output shift, but only on the single laser diode operation without the actual system operation in the high power laser system as in this journal. So this research provide high fidelity diode modeling to understand the thermal interaction with the 4 diode parameters. What is the impact of the thermal to the output performance of the system. So the method used in this journal is they define the equations from theoretical analysis and to simulate the model and to compare or to study the interaction between the 4 diode parameters with the output performance, the system output performance. The result is 4 junction temperature dependent do impact the optical power, but we observe that the wavelength is the center wavelength has the most significant effect on the output power. So since we see when we go to case 3, we see spectral power density is degrade significantly when we add on another 3 diode parameters. So as a result, so all the temperature dependent parameters need to be included in the simulation tools or the equations, so that to really obtain the accurate interaction between transient junction temperature interaction with the laser light output and the optical power output and the light intensity. This is the first journal. While second journal, the novelty is several technique is suggest to reduce the angle of divergence. 2 of it is select a heat sink that match the thermal expansion coefficient and tilted cylindrical lenses, custom refractive plate, and some others items. But in order to use this technique, there will be adding complexity on the system and potentially increase the cost and reduce the possibility of the commercial opportunity. So with this paper, in this paper, so there's 2 That's a very simple simple methodology or the concept, in an innovative way to reduce the angle of divergence, with large mount. So in this way, will increase the chance of commercialize and to obtain a better performance. And the method of this journal is to define equation and to do model simulation, and again to compare with the experimental results. So the result is dual half BTS is able to reduce the angle of divergence. This is really is clearly reduced in parabola shaped smile as well as S-shaped smile. So the also when angle of divergence reduce, the optical efficiencies, the coupling efficiencies is increased by more than 85%. Okay, and thirdly, the experiment versus the simulation result is comparable, so it's consistent in fast axis residual angle of divergence comparison between both. Okay, well, for third journal, the novelty part is the asymmetric waveguide structure with optimized P waveguide layer thickness is designed, and to obtain the power, the optimum power conversion efficiency. But the mechanism of achieving high power output was rarely explored theoretically. So in this work, we study different type of layer thickness, and to find out which one is the most optimized one to achieve the highest power output and conversion efficiency. So detailed mechanism was presented in this paper. Method is the same with the second paper, to define equation and modeling simulation and comparing with the experiment. Result is the optimized layer thickness with maximum output are obtained, okay, with 550 nanometer. So experiment and simulation, one side is consistent in the power and injected current is consistent is in by comparing experiment and simulation, but on the other hand, there's a lack of consideration of some losses, in threshold current, so that we see some differences in threshold current. One is 0.65, another experiment is 0.85 ampere, which is a worsened case. So these are the overall conclusion of each journal. From the first journal, so among the 4 parameters, as we can see, center wavelength has the most significant effect of the output optical energy over an entire pulse. So while the other 3 has a very small influence, but there is still influence. So in certain application, optical power loss can be acceptable, but decrease in light intensity is not acceptable. And as you can see, when we include all 4 diode parameters, spectral power density is degraded significantly. So this will affect the performance of high power laser systems. So in order to achieve more accurate, the accurate in the output performance, we need to include all 4 temperature dependent parameters to really understand the junction temperature in interaction with the light output and the intensity. Second journal is talking about the reducing in angle of divergence. So again, simulation and experiment has been set up and compared with a very large amount of the laser diode bar. So with the help of half BTS, it's possible to shape the beam so that to achieve smaller angle of divergence and increase the higher brightness or in light intensity. So according to GMAX simulation, the angle of divergence can reduce by more than 40%. So in conclusion, we can significantly reduce the angle of divergence and by using a half BTS. So we believe this can increase the brightness of commercialized laser diode array that bring significant improvement in coupling efficiency. So the third paper conclusion is simulation calculation has been carried out by optimizing the layer thickness to 550 nanometer from simulation, and after that we compared to the experimental results by fabricating device of 550 nanometer. Okay, then we do see by this layer thickness, the FW full wave half max of divergent angle is increased from 26 to 28, and the electrical to optical conversion efficiency of 60% and output power of 5 volt are obtained when draft current is 5. The simulated result will provide theoretical support by optimizing the waveguide layer thickness. So in our case, the optimized one is 550 nanometer, and this is proved to improve to achieve the maximum output power and optical characteristic, which are applied to edge-emitting laser. So in summary, all three journals have their own novelty, but my preferred journal is the second journal, which is the reducing beam divergent angle by using a dual half BTS the system. So because firstly, the author did really consider on the production complexity, which really save the cost applicable to a current manufacturing, and which give a commercialized opportunity. And secondly, is really a simple and low cost yet innovative technique, but it actually bring a huge improvement in beam divergent angles, reducing the divergent angle and thus improving in the coupling efficiency. So lastly, the experimental results is also consistent with the simulation results, so which indicate that the technique is accurate and as well as achievable in future. So when compared to first journal, so first journal is just do a model simulation without practical experimental for result proven, while the third journal, the experimental result is slightly incomparable, different to simulation results, which indicate there's some estimation with accurate information or estimate in their estimation. So my preferred journal will be the second one. Thank you.